So in this chapter, chapter 8, we are going to be computing confidence intervals for different parameters. In this case, in part 1 of section 8.1, we're going to look at the population mean, mu. And this is going to be for a known value of sigma. This is important, known. So our objectives are to construct and interpret a confidence interval for a population mean when the population standard deviation is known, find the critical values for the confidence interval, and then we're going to use technology to find the confidence intervals. So in this chapter, it's going to be important to have terminology. A point estimate is a single number that is used to estimate the value of a known parameter. In this case, for a quantitative variable, x bar is going to be our point estimate. A confidence interval is used to estimate the value of a parameter. In this case, the parameter of interest is mu. And so our confidence interval is going to be our point estimate plus or minus something called the margin of error. The confidence level is the percentage between 0 and 100% that measures the success rate of the method used to construct the confidence interval. We're certainly going to get into that soon. The margin of error, which we've just talked about, is multiplied by a critical value z by the standard error. So our first objective is to construct and interpret a confidence interval for a population mean when the population standard deviation is known. So we start with an example. A simple random sample of 100 fourth graders is selected to take part in a new experimental approach to teach reading. At the end of the program, the students are given a standardized reading test. On the basis of past results, it is known that the scores on the test have a population standard deviation of 15 points. The sample mean for the scores of 100 students was 67.30 points. The administrator wants to estimate the mean score would be if the entire population of fourth graders in the district had enrolled in the program. The best estimate for the population mean is a sample mean, 60.30. The sample mean is a point estimate because it is a single number. It is very unlikely that x bar, 60.30, is exactly equal to the population mean mu of all fourth graders. Therefore, in order to estimate to be useful, we must describe how close it is likely to be. For example, if we think that it could be off by 10 points, we would estimate mu with an interval between 57.30 and 77.30, which could be written as 67.30 plus or minus 10. We call the plus or minus number the margin of error. So we're going to go through finding a 95% confidence interval. We need to determine how large to make the margin of error so that the interval is likely to contain the true population mean. To do this, we use the sampling distribution of x bar. Because the sample size is large and greater than 30, the central limit theorem tells us that the sampling distribution of x bar is approximately normal with mean mu and a standard error of sigma over the square root of n. For the teaching reading example above, the standard error is 15 divided by the square root of 100. Now we construct the 95% confidence interval. We begin with a normal curve under the z-scores that find the bounded middle portion of the 95% area under the curve. The z-scores are 1.96 and negative 1.96. the value 1.96 is called the critical value of z. To obtain the margin of error, we multiply this critical value z by the standard error. So the margin of error is the z value for the critical value times the standard error, which is 1.96 times 1.5, which is 2.94. A 95% confidence interval for mu is therefore the point estimate, which is 67.30, minus the margin of error, which is the lower bound of our estimate, to the upper bound of the mu estimate, which is 67.30, plus the margin of error of 2.94. And so we are confident, 95% so, that the population mean is between 64.36 to 70.74. So what is our meaning of the confidence level? Well, based on the sample of 100 fourth graders, using the new approach to teaching, a 95% confidence interval for the mean score was constructed. 95% is the confidence level for the confidence interval, the confidence level. The confidence level measures the success rate of the method used to construct the confidence interval. If we were to draw many samples using each one to construct a confidence interval, then in the long run, the percentage of confidence intervals that cover the true value mean would be equal to the confidence interval. So in our case, suppose we had 100 samples, and of the 100 samples, we constructed 95% confidence interval for each of the samples that we had. We did just one before. We would say that 95 of those samples covers the true value of the mean mu, and 5 of those values would not. So therefore, the 95% confidence interval is telling us that 95% of the samples that we gather would cover the true value of mu, whereas 5% would not. So how did we get started with this idea of confidence intervals? Well, it was taken by statisticians that they called something called the sampling error. The sampling error is the absolute difference between the point estimate and the parameter of interest. So we have a formula that says the sampling error is the difference between x bar and mu. If the point estimate is a good estimate, then the sampling error is minimized, which means that the closer to 0, the better. So once we set this sampling error up, the idea was the confidence interval came from this particular idea. So when we are using the sampling distribution for an estimate, the sampling distribution of all possible samples from the population, each point estimate from the sample must lie within the sampling distribution. Thus, a distance between the point estimate and the parameter mu can be calculated using the z-score to find the number of standard deviations the point estimate is from the parameter. So we know we can use the z-score to calculate the distance between x bar and mu. We call that the standardized distance when we divide it by the standard error. Now, when we multiply both sides of the equation by the standard error, we get that the sampling error, which is the margin of error, equals the absolute value of x bar minus mu. Well, whenever we take the inside portion of the sampling error, this can either be negative or positive. X bar could be less than mu, or x bar could be greater than mu. But because it's an absolute value, the value is always considered positive. When we take off the absolute value signs, the margin of error now becomes a plus or a minus situation. So now the margin of error, once we take the absolute value off, we get a plus or minus margin of error. You will see that now we have a plus or minus margin of error is equal to x bar minus mu. And now we can rearrange the terms. We can move mu onto the other side and plus or minus m to the other side, and you see we immediately have a confidence interval. So from our last picture, we had the idea that mu is equal to x bar plus or minus m. We just rearranged the terms under the last slide. Well, what does that actually mean? Well, it means we have an upper bound. Here is our upper bound. X bar plus z times the standard error, which is our margin of error, is our upper bound. And our lower bound is x bar minus z times the standard error. So, if z is now related to our confidence level. We find z finding the area under the sampling distribution curve. So in this case, an area of 95%, z would be a negative, it would be a 1.96 value. So now our objective 2 is to find critical value z for various confidence intervals. Although 95% is the most commonly used confidence level, sometimes we want to construct a confidence interval with a different level. We can construct a confidence interval with any confidence level between 0 and 100 by finding the appropriate critical value for that level. The critical values for several common confidence levels are given at the bottom of row A3. So for 95%, we see it's 1.96. If we wanted the critical value between 99%, we would see it's 2.576. So here's an example. A large sample has a mean of x bar equals 7.1 and a standard error of 2.3. Construct a 90% confidence interval for the population mean mu. From the bottom row of A3, we see that the critical value for a 90% confidence interval is 1.96. So the margin of error is the critical value, z, which is 1.645 times 2.3, which gives us a margin of error of 3.8. So now we get the upper and the lower bounds of our estimate, which x bar in this case is 7.1 minus the margin of error of 3.8. That's our lower bound. And our upper bound on the confidence interval is 7.1 plus 3.8. So, guess what? There is the final result. Our confidence interval is between 3.3 and 10.9. Sometimes we may need to find a critical value for a confidence level not given in A3. To do this, it's useful to learn a notation for a z-score with the given right to the area. So the notation z alpha refers to the z-score with an area of alpha to its right. and you can see that in the picture we have a z alpha over 2, and typically for confidence interval, because there's an upper bound and a lower bound, we'll be referring primarily to this notation of z alpha over 2, so that the area is that we're looking at is to the right of alpha over 2. So if 1 minus alpha is the confidence level, then the critical value that we're looking for is z alpha divided by 2, because the area under the standard normal curve is between a negative z alpha over 2 and z alpha over 2. These z-scores can be found using table A2 or the technology piece. So suppose we want to find the critical value for a 92% confidence interval. We notice that for the confidence interval, we get 1 minus alpha is equal to 0.92, and so it follows that alpha, when we solve that equation, we get alpha is equal to 0.08, and we divide it by 2, we get 0.04. So the critical value we are looking for is z at alpha 0.04. Since the area to the right of z 0.04 is 0.04, the area to the left is 0.96. So either using A2 or technology, we find the critical value to be 1.75. So here on the table, we go inside the table, right? And then we look at what the z value is. Again, if we were going to use technology, we use the inverse norm. We put the value of the area to the left of z, and then this is mu, and then this is, of course, the standard error, which is in this case 1. The method described for a confidence interval requires us to assume that the population standard deviation sigma is known. In many cases, sigma is not known. We may make this assumption because it allows us to use familiar normal distribution. We will learn how to construct confidence interval when sigma is unknown in the next section. Other assumptions for the methods described here for constructing confidence intervals is that we have a simple random sample. And the second assumption is the sample size is larger than 30, or the population is approximately normal. So here we have an example. A machine fills cereal boxes. It's supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. It is known from past experience that the fill weights are normally distributed with a standard deviation of 0.2 ounces. Construct a 90% confidence interval for the mean fill weight. First, we check our assumptions. The sample is a simple random sample and the population is known to be normal. The assumptions are met. The point estimate in the sample is our x bar, which is 20.25. The desired confidence level is 90%. By table A3, the critical value appears to be 1.645. The standard error then is going to be 0.08165. So the margin of error is going to be 0.1343. The 90% confidence interval, therefore, is the point estimate plus or minus the margin of error. So the lower bound of our estimate is 20.25 minus 0.1343, and the upper bound is 20.25 plus 1.1343. And so our final result is we are 90% confident that the mean weight, mu, is between 20.12 ounces to an upper bound of 20.38 ounces. So doing things by hand is a little tedious. We can use the TI 83 or 84. If you hit the stats key and you move the cursor over to test, you will find that the option we're looking for is under option 7, which is called the Z interval. We only use the Z interval if we know the population standard deviation, sigma. If the summary statistics are given the stats option, we should select that option. So in this case, in the case above, we'll probably only select the stat option. If the raw data is actually given to us, we'll select the data option. So again, we're going back to the machine that fills cereal boxes. In this particular case, a random sample of 6 boxes is found to contain the mean of 20.25 ounces of cereal. And it is known from past experiences that the weights are normally distributed. That's an important piece, with a standard deviation of 0.2 ounces. It should say a population standard deviation. Construct a 90% confidence interval for the mean weight. Well, we press the stats key, we move over to the test key, and we select option 7. Then we select the stats option because all we have is statistics. We don't have an actual data set. We enter 0.2 for sigma. We enter 20.25 for x bar. We enter 6 for the sample size n. And our confidence level, we enter in 0.6. We hit calculate, and then guess what? We get the answer. We get a lower bound. Here is our lower bound of 20.12 ounces, and the upper bound is 20.38 ounces. So that concludes this particular portion of part 1 of chapter 8.1. We learned how to construct and interpret a confidence interval for population mean when the population standard deviation is known. We learned how to find critical values for confidence intervals, and we used our TI 83 to calculate these confidence intervals. Please move on to part 2 of this section.